Wait, are we going? Oh, okay. Well, hey. Uh, hey everyone. I'm John. Feel free to grab some pizza, sit down, quiet down, shut up. And I'll be talking to you about monads today. It's going to be a very exciting time for all of us. So the best place to start with anything really is the definition. And a monad is simply a monoid in the category of endo functors. So I guess with that, I'm going to open it up for questions. If you guys have anything that you need to kind of dig in deeper, let me know. Okay, well, okay, let's try again. So if we were to Google search what monads are, we get a lot of responses, but unfortunately, only one of them is correct. And so instead of playing this game of asking absurd questions of what monads might be like, let's just try to do them first. And then we'll talk about learning by actually learning and figuring out what they really are, but sometimes it's easier to see things first. Am I in? Okay, whatever. So we're going to do both. It'll be great. Por qué no los dos? So monads by example. This is the identity monad. And you might be thinking, ew, what is that code? You're right, it needs more object orientation. So we're not going to use Haskell in this talk. We're going to keep it into things that people here have seen more often. Specifically, we'll be using TypeScript, which is basically a lot like JavaScript and Java together. So this hopefully makes a little more sense. This is the identity monad. There's a lot going on here for how little it does. So we have this variable typed inner value. We can store something of any type. Doesn't really matter. We can construct an identity monad by just wrapping around this value. All we do is we take it and we store it internally. And then we have this very nasty function down here. It's called bind. And what bind does, and let's read it across, it takes in a function whose parameter is of type T and returns an identity monad of type U. So what really this is saying is I'm going to give you a function that I want you to pump the inner data value into. And it's important that at the other end we may not get back out the same type. So if I have an identity monad of an integer, I might get back an identity monad of a string. That's totally cool as long as it's still an identity monad. And it's a very simple function. The type signature is a little complex. And so in practice, what this looks like is we can construct an identity monad, we wrap around a value, and we can bind functions against it. Important things going on here, we are not mutating any values. So when we do a.bind with this function, we get back a new identity monad. The old one stays the same. And again, here we combine with a function that is going to return something of a different type. So this looks kind of ugly. I hate writing new identity monad on literally every line. So you can use a thing called fmap, which is basically exactly the same, except it does that new identity monad for you. See how it's basically the same function, but we wrap it in new identity monad to save ourselves some time and effort. And so we sacrifice the ability to construct the monad, which in this case is pretty useless, in order to get something that's more terse and easier to read. Again, we still really haven't done a whole lot. We've written a lot of code, and it does basically nothing. So but we do have some things going on here. We have a way of ordering functions, which isn't that exciting, but it's there. We have a context. There's a state being maintained under the scene. Behind the scenes. And the biggest thing here is we have the control of function application. We're doing nothing special with this right now. But since we take in the function, we get to choose how it gets called. And we'll see some of the power of that in the maybe monad. So the point of the maybe monad is to handle things that may or may not exist. Similarly, you can think of objects that may or may not be null. Now, the maybe monad has this sum right here is exactly the same thing we had before with our identity monad. All it does is call f on the inner data, it stores an inner data, and that's all. But we also have none now, and they both implement the same interface, so we can talk about them together. And what none does is when I give it a function, it just gives me back none, because I can't call a function on nothing, I have to have something. Again, this will make a lot more sense now that we can see it in action. So let's define two helper functions real quick. Half, which will say, OK, let's take in a number. If the number is not even, it has no half. We're going to deal with integers. So 5 has no half. But if it's even, then we'll divide it by 2 and return that back out. If it's not, we return none. And we also have this plus 1 here. And what plus 1 does is it just adds 1. Pretty simple. So now we can start binding like we did before. Again, not that exciting. But we'll see here that when we bind half first and then bind plus 1, no error is thrown, despite plus 1 not being able to be called. And that's OK. We called bind half on sum 5. Sum 5 is odd. It doesn't have a half. And so it became none. And it just propagated through to the end. But in this case, if we added 1 and then divided in half, we got our 3 back out. Again, baby steps. We're getting somewhere, but this isn't that exciting. But what we do have now is this model for talking about railway-oriented programming, which is a pretty cool concept, which is that we can keep going as long as things are successful, but we can dump into a stop state at any point along the way. And that's what this none is. Once we're at none, we failed, we have nothing, but the program keeps running and no one's the wiser. But that's, again, not that great. If my program just returns none, I'm like, well, that's not helpful at all. I don't know why it returned none. So we can add an error message into this none, and then it becomes the result monad, which is for things that may or may not succeed versus things that may or may not exist. And all we do to change this is success is the same as sum before. It's the identity monad. It just keeps doing what it did. But fail, what it does is it just propagates its value forward forever. So as soon as I hit my first error, it's the error that slides down to the end. Every time I apply a function, the function never gets run. I just forward the error down the line. So now instead of returning none when we try to divide an integer in half, we can now say we're failing because it was odd. So when we come down to this end of this bind pipeline, we can say, oh, look, B was a failure with the error message odd, which is really cool because now we have essentially error handling without any kind of stack unwinding or try-catch semantic, which is very, very cool. It is. It's cool stuff. And there's way more types of monads out there. This is a very simple one. Other monads include linked list. Linked list is a monad. Its inner data stores a value and the next or previous, depending on how you want to implement it, node. Haskell's I/O is implemented as a monad. It stores a handle on the real world and a current value. And then Java Streams composes functions into a processing function. If you haven't dealt with most of these before, it's not going to mean a whole lot to you. But it's to say monads are actually used even in Java and in a lot of places. So now that we have the fact they're not that exciting, they're pretty simple classes, let's make it harder because we can. So now we come back to our definition that we had, which is kind of painful. There's a lot of multisyllabic words, and we're not really sure what most of them mean, if any. So let's take them down one at a time. But first, let's talk about some category theory. So category theory, you might recognize category was one of the words used in there. And a category is pretty simple. A category is something that stores objects and morphisms between those objects. It is not a set. The morphisms are not functions. They're just this generic idea of things and ways to go from one thing to another. And they're composable. And that's it. And so a selection of these objects and morphisms is called a category. Cool. But if you really want to think about it that way, you can think of morphisms as functions. Just don't tell anyone I told you to say that. So category is not that complex. It's just things and functions. And so now we're going to talk about a functor. We use the word Endo Functor in our definition. It's a bit more complex than a functor, sort of, maybe simpler. But we need to know what a functor is first. So if we have a category A, which we saw in the previous slide, which stores objects and morphisms, we can then apply a functor, which will move, or map actually, every single object and morphism into another category such that all of the relationships hold. Really what this means is for every x, there's a functor, there's an f of x. And then for every function f, there is a ff. And these relationships still hold. The fact that I can go from x to z via f of g still holds under the functor, which is great. And so the official mathy definition of a functor without a diagram looks a bit like this. It's that we map every object, that morphisms are preserved, and that composition is preserved as well. We saw that with pictures. It's way easier with them. So an endo functor is actually just a functor that maps back onto the same category. So for every x that's in the category A, f of x is also an A. The functor applied to x may be y. Who knows? Who cares? As long as it's back inside A. Same with functions. Functions always map back into A.